Hello, this is your 19th lecture for the Psychology in Action module, and another one that is narrated for you because we're all off being quarantined. Today we're going to have a look at chi-squares. We'll also touch on parametric and non-parametric tests. When we get on to chi-squares, not only will we look at when it's appropriate to use that type of statistic in mathematics, but also how you would go about working out calculating chi-squares. And then we'll finish up looking at a little bit around your experiment and how you're actually going to carry that out, particularly now that we are in this quarantine situation. Now, before we get on to the chi-squares, you will need a calculator, and I'd also recommend having some scrap paper and a pen or pencil. So if you want to pause this recording and run off, get your calculator. If you don't have an old-fashioned calculator, then your mobile phone will almost certainly have a calculator function on it. And get yourself a pen and some scrap paper. And then when you're ready, restart the recording. And so hopefully now you've got your bits and pieces and you've restarted. So first off, the difference between parametric and non-parametric tests. Well, a parametric test, which is something like a t-test, for example, and we'll be doing one of those next week. So you don't need, well, we'll get onto that then, so I don't need to explain it too much now. But when you're doing a parametric test, there are different types of statistic, some of which are parametric and some of which are non-parametric. The ones for parametric tests assume that your participants, the people who took part in your experiment, all came from a wider population of individuals who have a fairly normal distribution of features about them. So, in other words, they're fairly average, ordinary, standard people. There's nothing particularly weird or bizarre or unusual about them. That they're a standard group of people. And so you would use a parametric test if that were the case. However, if the people you are experimenting upon are in some respects either known to be unusual in some way, so there is some feature about them that the majority of people in the wider public don't share. So, for example, they might have an unusual rare illness, or they might all have PhDs, because obviously the vast majority of people don't have a PhD. There's something about them that makes them set apart, or you simply know nothing whatsoever about the wider group of people from whom these individuals you've experimented on are drawn. So you don't really know if they're normal, not normal, or what they are. They're a bit of a mystery. So if that's the case, you'd use a non-parametric test, and chi-square is one of the non-parametric tests. There are others, but we'll go on to those later on, so we don't need to think about them too much at this stage. And so you've decided, or at least I've decided for you, that you need to use a chi-square for this type of test, and we're going to look at some imaginary data in a minute. It's just been made up data, so that you can get an idea of how the chi-square works. Now, as I said, there are other non-parametric statistics out there aside from the chi-square. So if your experiment uses categorical data or ordinal data, and just in case you've forgotten what they were from a few weeks back when we spoke about them, categorical data is, for example, things like hair colour. So everyone who was a blonde, you ticked box 1. If they were ginger, you ticked box 2. If they had grey hair, you ticked box 3, and so on. So you've placed those people in a category, and that category is represented by a number, but the numbers are relatively random. They just symbolise categories of something like hair colour, or ethnicity, or religion, or some factor of that sort. Or ordinal data. Now, ordinal data, you remember, hopefully, is where you put things, scores, in order of how they came. So the example we gave a few weeks ago was a race. Now, either a foot race or a horse race or what have you. The person who came first, the second person, the third person, the fourth person. So you'd be putting them in order in which they came in a race. Or let's say you've given them all a spelling test. You could put who got the most right, they would be first, who got the second most right, they're second, third, fourth, fifth, and so on. So you put them in order where they scored in some kind of assessment or another. So if you're doing either categorical data or ranked data, then chi-square is ideal for this. If you're looking at other forms of data, for example ratio or interval data, then you would use a different type of test. But we will be getting on to what those different types of tests are later on in the lecture series. So we've decided, for the sake of this lecture, we're going to look at the chi-square and how to use that. So when would you use it? What would you do with a chi-square? Where you would be looking at two variables and how those two variables relate to each other. Now these variables are not necessarily independent variables and dependent variables. There's different types of variables we could be looking at, but you're seeing, is there a relationship between them? So is there a positive relationship when one goes up, the other goes up? Is there a negative relationship? Is there some other type of relationship between these variables? And the data you're looking at is going to be either categorical, as we said, or ordinal. The design is an unrelated design, so you've got, rather than the same group of people doing everything once and then doing it all under a slightly different condition, like doing a memory test when it's a nice quiet room and doing a memory test when it's a very noisy room. That's not the type of design you're looking at. So you're looking at people who have scored in one condition but not participated in a different condition. So for example, let's say you've got a bunch of people together and you've asked them, do you like sweets or do you prefer crisps? And some of them will have said, oh, we like sweets, and some of them would have said, oh, actually I don't, I prefer crisps, I like savoury stuff. So those are two factors you looked at, sweets versus crisps, and then you split this group between the men and the women. So as you can see on the grid there, 7 men preferred sweets to crisps, 14 women preferred sweets to crisps, 11 women preferred crisps to sweets, and 20 men preferred crisps to sweets. Nice and straightforward. Just 4 numbers we need to think about here. Now each of the boxes there is normally referred to as a cell rather than a box. So just bear in mind, when I say cell, I'm not talking about prisoners and jail bars, I'm just talking about a box on a grid. And what we have in the boxes on the grids are frequencies. So it's not a percentage, what percentage of men like sweets, what percentage of women like sweets. This is simply 7 men, 14 women. We're not looking at how that forms a percentage of a much larger group. We're just looking at frequencies, how many people ticked this box, how many people ticked that box. Okay. So far, hopefully so good. So that's the sort of data we are going to be using as we go ahead. Now the same grid again appears here, and this is referred to as a 2 times 2 chi-square because you've got 2 boxes on the vertical column, sweets and crisps, and 2 boxes on the horizontal column, male and female. If you had somebody who said that they were neither male nor female, then you might be looking at 2 times 3, but we're not, we're looking at 2 times 2. There are bigger chi-squares that can be looked at, but we'll stick to this one for the moment. So far, hopefully, so straightforward for you. If we wanted to look at a 2 times 3 one, on this occasion we've got people who prefer sweets, people who prefer crisps, and people who either don't like either or like both equally the same. So they don't have a preference one way or the other. And of the people who ticked the prefer neither, we don't actually know whether it's that they like both the same or that they can't stick either. We just know that they don't have a preference. And so you've got 15 men and 10 women who tick the don't have a preference one way or the other. If we're looking at a 2 times 3 one, what we can speculate by doing the maths is whether or not there is some sort of relationship going on, but we can't predict which direction the relationship is going in. So when we get on to observed frequencies and expected frequencies, what we're looking at is a pattern between what you would expect there to be in any given survey, or a survey about crisp preferences and sweet preferences, or whatever the thing is that we're looking at. What would you expect the results to be versus what they actually are? So the observed results are what they actually were. So going back, the observed results here were 7, 14, 20, 11, 15 and 10. That's the number of people who ticked each box. That's the observed pattern, that's who said what. The expected frequencies, well, that would depend on the nature of what it is we're looking at, but roughly how many people on average would you expect to tick a given box? Well, the way a chi-square works is that the assumption is that no more than 20% of the expected frequency count should be below 5. So if it's below 5, there's something unusual going on there. How do we work this out? Well, we start off, we think about the null hypothesis and the hypothesis. Now, it's going back quite a few weeks since we spoke about this, but hopefully you'll remember some of it, it'll come to mind. The hypothesis is what you think is likely to happen. You're expecting your statistics to go one way or possibly to go another. A null hypothesis is that nothing much is going to happen. So in this case, the null hypothesis will be the population, that is to say the number of people in each of the cells on your grid is going to be in the same proportions as expected. So you make a prediction, I expect it to be this, and if the actual figures are exactly what you expected them to be, the null hypothesis is upheld. If the actual figures are quite different from what you expected them to be, then the hypothesis would be upheld. The bigger the difference between expected and observed data, the more significant the chi-square factor becomes. Potentially big enough for it to be significant, whereupon when you were doing your write-up in the report you would say you had found a noteworthy pattern, that you'd found an issue of significance that wasn't just random chance, random fluke, there was a pattern going on of some sort. So, forget about crisps now and sweets. This particular table, we are looking at people who go to university. Now, are they the first person in their family to go to the university, or are they second, third, fourth, 310th person in their family to go to university? So we have a box for people who are the very first members of their family to go to university, and another box, a set of boxes rather, for people who are not the first. They could be, we don't know if they're the second person, third person, 10th person, what they are, but someone else in their family has gone to university before they did. Could be an older brother, sister, could be a parent, grandparent, great-great-great-grandparent, who knows. Now, having worked out whether they're the first or not the first, we then look to see, did they stick with the degree, go through, reach graduation, get their bachelor's degree at the end of it and walk away with a big smile on their face, or did they drop out? So on this one, 9 people who were first generation students dropped out, and 11 people who were first generation students stuck with it and graduated and went laughing all the way into a future career. Whereas of those people who were not the first members of their family to go to university, 7 of them dropped out and 12 of them continued all the way to graduation. So just 4 numbers to look at here, nice and straightforward. Well, hopefully you'll think it's nice and straightforward as we go along. Now there is a formula there. So x squared equals the sum of O minus E squared divided by E. And I dare say some of you will thump your head against the wall at this stage, but bear with it, because I'll explain this formula and we will go through it one stage at a time. And by going through it one stage at a time, that will make the process much easier than just staring at a somewhat confusing looking formula that might not mean a lot of anything to some of you, possibly a lot of you. We'll go through it. So what do the O's and the E's and so forth stand for? The O is the observed frequency in each cell, so the actual number. So going back here, 9, 7, 11, 12, they are the actual numbers in each cell. So O would represent one of those four numbers in a formula. E, so O minus E, the E is the expected frequency in each cell. What would you expect them to be if this population were just average with no particular patterns, no particular relationships of anything, it was just going along. So now we know what the O's and the E's stand for. We'll start to work our way gradually, step by step, through this formula using the numbers from that grid there. Okay, so I don't know if you might find it easier if you just scribble down on your scrap paper that grid 9, 7, 11, 12, so you can keep track of it as you go along, or as we go along in this video. That might help. So if you want to pause the video, scribble these numbers down. If you don't, fair enough. But give you a second to pause it, and then once you've written the number down, click play again. Okay, step by step. So there are 4 steps we'll go through. Some of these I've broken down into different sections, but 4 main steps we'll go through. So first off, we give each cell a letter, remembering that cell here just means one of the boxes on the grid. Step 2, we calculate the expected frequencies. So the average expected frequency, not what was actually scored. Then we square factor x, we square x, the sum we're looking towards, and then we calculate the degrees of freedom. Now, the degrees of freedom are a reflection of a statistic that we'll explain in more depth as we go along in the course. We have touched on them very briefly, but we'll come back to them in more depth in the future. But today we're just looking at the mathematics involved, rather than any deeper understanding at this stage. So, first stage of this, give each cell a letter. So we're just going to call them A, B, C and D. Nice and easy, in red there. Well, unless you're colourblind, I don't know what colours that would look like if you're colourblind, but if you're not, 9 is A, 7 is B, 11 is C, 12 is D. So nice and straightforward, and if it helps, scribble that down on your bit of scrap paper. Okay, now we need to calculate the row totals and the column totals, and then work out the overall total. So, explain this step by step. So it's already done for you, don't actually need to do any maths here, just to make sure that you're following what you add to what. So we'll start with that row that says dropped out. So we add cell A to cell B. In other words, we add 9 to 7, and what we get in the totals column on the far right hand side is 9 plus 7 equals 16. On the did not drop out row, we go C plus D. In other words, 11 plus 12, which gives us a total of 23. And if we add 16 to 23, we get the total number, n in brackets, of 39. So that's how many people have responded. 39 people have responded to this survey about who stayed the course, who dropped out, and so forth. Now we also have to work out the numbers for the columns as well as the rows. So the columns go down, the rows go across. So the column that says first at the top, we are adding A to C. 9 plus 11, which gives us 20. And the column which has other at the top, we're adding B to D. 7 plus 12 gives us 19. And just to double check, if you add 20 to 19, you should still get 39. If you suddenly find you're getting another number, then somewhere along the line you've pressed the wrong button on your calculator. So far so good, hopefully. Now, this looks a little bit involved, but if you just focus on one bit at a time, and don't get overwhelmed by all of the numbers, just one bit at a time. So we're now going to work out the expected frequencies, in other words, what we would assume might be the average score in each of the cells on the table, rather than what the actual scores are. So the expected frequency of the different rows. So we'll start with the dropped out row. So we're looking at A here. So we find 16 by 20. Okay, so if you look on the numbers in the left-hand side of the screen, where it says A equals 16 times 20. So where do we get the 16 and 20 from? Well, 16 is the number in the total row on column A. Sorry, not column A, row A, rather. So the drop-down row, you go across that 16, and also looking at the column, the vertical one, with A there. At the bottom, the total is 20, so it's 16 times 20. And if we do 16 times 20, you might want to do this on your calculator, and if you would like to pause this whilst you press buttons on your calculator, feel free, and then restart when you've found the answer. Or if you're very quick at pressing buttons, you might already have found it. 16 times 20 works out as 320. We then divide that by 39. Why 39? Because that's the total number of people who've taken part in this experiment. If you remember, we just worked out n equals 39. So it's the sum of row A and the sum of column A, 16 and 20, times each other gives 320, divided by the total number of people taking part, 39. And the answer already on the screen for you there is 8.205. And hopefully that is what you've just worked out on your calculator. So for B, 16 times 19, so if you locate box B on the chart, on the grid there, box B, the total number there at the end is again 16, and the total number at the bottom of the column this time is 19. So we do 16 times 19, and then we divide that by 39, and what we end up with is 7.795. Likewise, if you locate C on the grid, going across horizontally, you find the number 23. Going down vertically, you find the number 20 at the bottom. So 23 times 20, if you want to do that on your calculator. So 23 times 20 would give you a result of 460, and then if you divide that by 39, that would give you 11.79. If you're doing it on the calculator, it actually gives you a lot more decimal places. It's 11.79487179. But not what we normally do is round up to 3 decimal places. That's to say 3 numbers on the right hand side of the decimal point. So because it's 11.7948, 48 we round up to 5. So what you've got on the screen is 11.795. Okay, and locate D on the grid, go along horizontally on the row, the end number is 23, and go down on the column, and the bottom number on the column is 19. So if you times 23 by 19, what you get is 437, and then if you divide that by 39, what you get is 11.205 and a load of other numbers, but we ignore the other numbers and just round it out, or we don't even need to round it up on this occasion, to the first 3 decimal places, and it's 11.205. So far, hopefully, so good. If you're struggling with any of the maths at this stage, or at any stage actually, if you drop me an email or link to my college Facebook page and send me a private message on Facebook, then I can go back over this with you and explain it in a bit more detail. Okay, on to step 3. So we now check that the expected frequencies are all above 5. If none of the expected frequencies is less than 5, then you go along with the next stage of the maths. If the expected frequencies were less than 5, then you would abandon the chi-square as not, that the statistics wouldn't be viable. The results wouldn't be viable to use a chi-square. But on this occasion, they're all above 5. So when we say they're all above 5, just as a reminder, 8.205, 7.795, 11.795, 11.205. Now, I dare say some of you are going at this point because of all these numbers on the screen. But once again, we'll try and break this down step by step to make it manageable. So on your scrap paper, in your grid, if you, just to help you keep track of all of this, if you write in on each of the 4 cells, A, B, C and D, those running totals so far of 8.205, 7.795, 11.795 and 11.205. So just jot them in, either in a different colour or underline them or I don't know, whatever you want to do to make sure you can keep track of those figures. Now we're going to calculate x squared, and the sums you've got along the bottom of the screen there is one for cell A, one for cell B, one for cell C, one for cell D. We're going to do, well, they're already done, they're already worked out, they're already shown. But we're going to work them out, or I'll explain them as we go along step by step, and then you'll come to a conclusion. So when you see a mathematical formula, the ones on the bottom row, it's customary to do the bits in brackets first and then the bits outside the brackets afterwards. So you've got bracket 9 minus 8.205 bracket for cell A. And so we do that bit before we do any other bit. So if you, on your calculator, do 9 minus 8.205, and either pause this recording or if you're super quick with your fingers, you can do it. Excuse me. Once you've found the answer, you should have 0.795. Okay. If you haven't, possibly you just pressed the wrong button on the calculator by mistake. But 9 minus 8.205 equals 0.795. So we've done the bit in brackets. Now the little number 2 outside the brackets there, hopefully you'll all be flashing back to school. Some of you that's a longer flashback than others. And what you'll recollect is that tiny number 2 means you have to square a number. And to square a number, you times it by itself. So 5 times 5 is 25, 10 times 10 is 100, 6 times 6 is 36, etc. So what we times by itself is the number we've just worked out, 0.795. So if you times 0.795 by itself, 0.795 times 0.795, what you'll get, pause if you need to, what you'll get is 0.632025. We're going to use all the decimal places this time because we're getting a bit finicky with the numbers that we have developed. Now, you've got that straight line, the dividing line, drawn there. So we've worked out the formula, or the section of the formula rather, on the top of the dividing line. We're now going to use the number on the bottom of the dividing line, 8.205. Why is it 8.205? Because if you look at cell A, we've just worked out that cell A was 8.205. So what we now do is divide 0.632025 by 8.205, and it's important that you divide them in that order. So you divide the 0.6 number by 8.2, not the other way around. If you do it the other way around, you'll get a different result. So pause if you need to. Press your buttons. And what you should find as an answer is 0.077. And I suggest you scribble that down somewhere and keep track of that number. So just to skip forward to show you, 0.077 is what you found for A. Okay, now we'll do the next one on B, so still on that bottom row of sums there. So we do the bit in the brackets first. We do 7 minus 7.795. And what that gives us is minus 0.795. Now what we then need to do is times that by minus 0.795. And that should give us the sum of 0.632025. Same as the previous one, you'll note. And then we divide that by the number underneath the straight line of 7.795. And that should give us a result. I'm waiting for you to pause if you need to pause the recording. And if you don't, it should give us a result of 0.081, which we flash forward to that screen, and there you can see for B 0.081. Okay, so we've done section B. Deep breath, swig of gin, strong coffee, whatever it is that you need to keep going. We'll move on to section C, cell C. So for cell C, bit in the brackets first, we do 11 minus 11.795, and that gives us minus 0.795 again, which we times by itself. So times that by minus 0.795, and that should give us, pause, not that you really should need to pause because you're going to keep getting the same answer again and again, gives us the same answer of 0.632025, which we've gotten for the previous two sums that we've just done. And then you divide that by 11.795. Which will give us 0.0535 and a string of other numbers, which we round up, and that gives us 0.54. So as you can see on that screen, C is 0.54. We're getting there. So hopefully so far you're getting the formula bit, that the 0 and E, how what 0 represents, or naught, sorry, not 0, what naught represents and what E represents in this case. So it's starting hopefully to make sense by now as how the numbers match up. And we're on to our last stretch, D, on that bottom line. So we now do 12, bit in the brackets, 12 minus 11.205, which gives us 0.795, and we square it, we times it by itself, so we times that by 0.795, which gives us, once again, you might have predicted this because it's happened 3 times in a row now, 0.632025, which we divide by the last number on this screen, 11.205, and that gives us the result of 0.056 and a string of other numbers which we ignore because we're only going to the first 3 decimal points. Phew! We might need another gin. Okay, so there we have the results of the 4 cells. 0.077, 0.081, 0.054 and 0.056. And now we add those 4 numbers together. You can do that on the calculator if you'd like. and what it will give you is 0.268, the number at the bottom of the screen there. So that is x squared. X squared equals 0.268. And now you jump for joy, run around the room, sing Hosanna, do whatever it is you feel like doing, because we have found that number. And you thought maths was hard. Now, just before you hit yourself on the head with the empty gin bottle, we move on to step 6, calculating the degrees of freedom. So a degree of freedom is a measure of movement from a central number. We've touched on this briefly in a previous week, and we will come back to this in a future week. But for the moment, we're just going to do the actual maths and not worry too much about the ins and outs of quite what degrees of freedom are. So the formula for working out the degree of freedom for a chi-square is the number of rows minus 1 multiplied by the number of columns minus 1. And this is a nice easy thing because there's only 2 rows and 2 columns. So the second line from the bottom there, df equals, to all the bits in brackets, 2 minus 1 times 2 minus 1. So we do the bits in brackets first, as you now all know, because I keep saying it to you. So 2 minus 1 is 1, and miraculously, the other 2 minus 1 is also 1. That's convenient. So essentially what we're doing is the sum of 1 times 1. At this point in time, some of you may be feeling so beaten over the head with mathematics, that seems nightmarish, but it's not, because we all know that 1 times 1 is just 1. So the degrees of freedom is 1, the number 1. Nice and straightforward. If it was a bigger grid, it would be a bigger number, but it's a 2 times 2 grid, so for a 2 times 2 grid, the degrees of freedom are always going to be 1. Okay, the p-value, this is the probability value, is used to work out whether something has happened by sheer fluke, sheer chance, or whether there is a definite pattern going on here. Something is happening. So we achieve a p-value and the probability value, which is worked out on tables that are published in books by very nice statisticians who get paid probably nowhere near enough to work out these things, tells us that it gives us a number, and that number signifies the likelihood of a result being a fluke or not being a fluke. So we go out and we acquire a book. I've saved you the effort of having to go out and acquire a book, although possibly you've already done this anyway. So this table here I nicked from a book called Introduction to Population Genetics. You don't have to have that particular book, there's all sorts of books that have the same charts and tables in. So this particular chart of numbers is for a chi-square specifically. Other statistics would use a different table, and we don't need to look at most of these numbers here. So on the left-hand column you'll see the letter D. D is degrees of freedom, which is that thing we've just worked out. And we're using P at the power of 0.05, which is the standard thing to use for the vast majority of tests. There are those other ones, 0.01, 0.001, but they are used for normally quite large sums and very finite measures. So we don't need to bother with those for the time being. So look at column D. Degree of freedom is 1. So you go down to where it says, in the D column to where it says 1, and then you read across to the column 0.05. And you will see that number 3.841 on the screen. At least I hope you're seeing the number 3.841 at the crossover between degree of freedom 1 and probability 0.05. So that's the magic number, 3.841. Now, did X, all that faffing about that we've just been through, equal 3.841 or more? If it was 3.841 or a number higher than 3.841, we could go, woohoo! We have found an exciting pattern. Well, maybe not exciting, but we found a pattern, a relationship between people dropping out of university or staying the course and whether or not they're the first member of their family to attend university or the second, third, fourth, whatever member of their family to attend university. However, the number we found, the x squared number we've just been all the way through to discover, was 0.268, which obviously is smaller than 3.841. It's a lower number. 0 point anything is lower than 3 point anything. And so we go, because all that maths, we've not proved a damn thing. There is no significant pattern to the numbers we've just looked at. So we have to say the null hypothesis is upheld and the hypothesis is rejected. There is no particular significant relationship, at least on that survey, between whether or not someone is first, second, third, fourth generation attending university and whether or not they drop out or graduate. No pattern at all, no relationship. It's all a bit random. There you go. We've worked it out, we've done it, but even if we haven't proved anything, you've gone through the maths, you're still breathing, possibly you're suffering from gin poisoning by now, but you're still breathing, you're still going, you have done it, you have accomplished it. If we flash back all the way to, where were we? There, the formula, which looked possibly too confusing for words at the start, you have done that, you have worked it out in its complexity, you have worked out what s squared is. So well done. Make yourself a nice strong coffee to recover from all of the alcohol abuse that you've gone through so far. And once you've got your nice strong coffee, you can come back and listen to this little bit. Now, had the world been normal, whatever the hell that is, had the world been normal, we would all be still sitting in classroom. You'd be staring at me thinking, what the hell is he talking about now? And we would be ploughing our way through experiments, dragging poor gullible people into a classroom to do awful, unspeakable experiments to them, work out statistical data, and then write up your report. At the moment, quite clearly, we cannot do that. We can't be dragging people into classrooms because we're not allowed into the premises. So what are we going to do? Well, there's a number of possible routes we can take, and I'm not sure which one to take at the moment, simply because the future is an unknown factor. I did get my crystal ball out and give it a good rub, but sadly it's a bit dusty and a bit murky, and I couldn't see what the future holds in terms of when we're going to be allowed back into college. Now, one option you can consider is to find people to participate in your test through social media, Facebook, Twitter, whatever else that you're on, and get people to do the test virtually. So rather than having to have them in a room, you could just set the test up so they can do it online, and then you can gather the results that way. Although that might be a bit involved and a bit convoluted. Another way, a somewhat simpler way forward we can do, is for you in your groups chatting to each other by WhatsApp or email or whatever method you prefer to use. You draw up your plans, you draw up your designs, you come up with your ideas for how your experiments will work. You tell me, again by email or whatever other means you prefer, and I will then imagine that I am a room full of subjects participating in your experiment, and I'll write up a random bunch of numbers and send them to you and say, this is the results of your experiment, pretend that you've conducted it and these are the results you've got. And then you sit there and you write up your report as if you had done the experiment for real, and then you conduct the statistical tests on the random numbers I've just made up off the top of my head and emailed across to you. And then I will treat when it comes to marking, I will treat your experiment as if it was all done legitimately, as will indeed the second marker, and the external examiner will likewise be all kind and compassionate and lovely and accept that you couldn't do the experiment for real because of the crazy circumstances we're in, and that this is the next best method. So if you give me a little bit of feedback by email or via my college Facebook profile, or appending a message onto the YouTube page where this podcast is uploaded, whichever method you prefer, let me know whether you would prefer me to just make up statistics for you, or whether you would prefer to try and conduct your experiment online. It may be possible, of course, that some miracle cure is found next Thursday and we're all back in college just after Easter and we can do the experiment normally then. That's possible. It might happen. Fingers crossed. So you could just sort of wait and see what the world is like after Easter and then make a decision on that one. Up to you. In the meantime, whilst you're umming and ahhing, hopefully within your groups you've already decided the answer to these two questions. If you haven't, you need to decide what the answer is. So have you worked out quite what aspect of language acquisition you want to test? For example, we looked at all those things last time we were in class. You could be looking at how peaceful or noisy a learning environment is, whether students learn better by understanding the meaning of words or not understanding the meaning of words, whether they learn better by being shown photographs of the things whose name they're learning, whether they learn better by speaking a word or by writing a word down, all of those sorts of things. You could choose one of them. Something connected to how people learn language, and make a decision about which foreign language or made-up imaginary language you want to utilise. The data level, that's whether you want to do ordinal or ratio or interval. Category learning, categorical data doesn't really come into this one, so it will be one of the other three. The other aspect to think about is, have you decided whether it's going to be within groups or between groups? So within groups, you get everybody in the classroom to do it under condition A, and then you get them, all of them again, to do an experiment under condition B. Between groups, you split the class in half. Half of the class does condition A, the other half of the class does condition B. Which of those do you want to do? So once you've made those decisions, if you haven't already, let me know, and that will start to shape the type of statistic you need to use. So once I know what all three groups are doing in terms of the setup for the experiment, I will then get back to you and factor into one of the future lectures advice on which type of statistic you need to use for the style of experiment you are planning to conduct. So think about it, discuss it through social media, and then let me know also through social media. So next week, which will definitely be online because we've got this 3-week shutdown, which takes us through to Easter, so the lectures between now and the Easter holidays will all be online like this one is. No idea what's going to happen after Easter, nobody does. We'll play it by ear and see. But we'll get on to how to lay out your laboratory report, the sections that you need to write it up in, all the different subheadings and whatnot. I'll explain to you how to use a t-test statistic in the similar way that I've explained this chi-square, step by step by step. And I'll get on to talking about some of Vygotsky's language theories to contrast them to Chomsky's language theories that we looked at the other week. Yep. I look forward to hearing your feedback, and hopefully I'll get to see you after Easter, all things being equal. But in the meantime, take care and let me know how you're getting on. Bye bye.